name is Philipp Hanich. I'm head of laboratory here at Cube Biotech, and today we're going to have a wonderful intelligent infusion masterclass with my dear colleague Michael. I'm going to introduce him in a minute, but first let me tell you about something about this series. Here at Cube, we are experts for membrane protein research, and we have this wonderful masterclass series where scientists all over the world can share their work, can get exposure, can connect with others in their fields, and receive feedback from expert and peers. We at Cube here, we do not only provide service for membrane protein, also soluble protein research, but we also have a huge portfolio of consumables. We produce agarose, mag beads, and everything you can think about here in-house, here in Monheim, in Germany. And so we know what we have and we know what we use, and we can produce the quality you need and want. And we can assist you in protein preparation, biophysical target, characterization, structure determination by cryo-UM, or we can help you with your assay development. And we are very proud that we are the biggest provider of the synthetic copolymers to 4 different families all over the world. And yes, before I introduce my colleague, let me tell you quickly something about how we do it here in this masterclass. We're going to hear the talk, and you can ask all your questions in the chat window. It's very easy. We're going to have a Q&A session right afterwards, and you can click on the blue speech bubble in the chat window, and you can just paste your question there, and then Michael is going to answer all of your questions right after his talk. In the event that there are too many questions and we run out of time, we of course are going to answer your questions by email afterwards. But let's just hope we're going to make this today. Now I will introduce my colleague, Dr. Michael Erkelenz. Sitting on my right side today is our chemist here at Cube Biotech, and one of our chemists. He has an academic and professional background in physical chemistry, even though he started out as a biologist, just like me in the beginning. But right after his master's, going to his PhD, he then went to the chemical side of business and specialized in nano biophotonics. In 2017, he started his PhD work, which he finished in 2021 at the University of Duisburg-Essen, where he focused on the development in advanced plasmonic DNA nanostructures within the nanophotonics field. That sounds very complicated.
Yeah.
And throughout this period, he conducted extensive work in the synthesis, functionalization, and characterization of gold nanoparticles. So to wrap it up, he's an expert in gold nanoparticles, and this you're going to hear definitely right now in his talk. So Michael, if you would like, please feel free to start, and I will give you the full focus of our camera here.
Yeah, well, thanks a lot for this kind introduction, and also welcome from my side to this masterclass today. So let me put on my presentation there. Great. Nice. Okay, so today is a nice day because I have the opportunity to introduce our new functionalization service for particles. So not only for micrometer scale agarose, but also for nanometer scale noble metals. So gold nanoparticles are an important topic in the recent or in the last years, and today I would like to introduce both functionalization services to you. So first of all, here at Cube, we have a great and really, really nice service facility, so which is also done or led by Philip. So we have on the left side the protein service, which includes soluble proteins and membrane proteins, and in general is from the beginning, from the scratch, from the gene to the end, to the structural elucidation of protein structures. It's all in-house here. So it's really, really comprehensive service that you can get here at Cube. So and now on the other side, on the right side, you see that we also have a custom functionalization service for particles. So for like agarose beads, for magnetic beads, and also for gold nanoparticles or other nanoparticles. So also iron, platinum, or silver is also possible. And this service I would like to explain you to today. So, but first, why we have this service? So, in the last years, we were able to successfully express, stabilize, and purify over 300 membrane proteins, which is quite a huge experience. And most of these purified proteins were possible because we are experts here in the purification technique and also in the development of own agarose or MAC bead affinity chromatography systems. So we also were able to purify like 230 projects of soluble proteins. So this is also possible. But most of the targets were GPCRs. In general, we have a 95% success rate for the membrane protein stabilization and purification, which is unique in this field. Well, so first I would like to give you an idea of the two most used systems in the protein purification world. So the first is, of course, the agarose affinity chromatography. So, for example, let's think about a cell lysate with your target protein, and you would like to isolate it from this lysate. So you have a stationary phase, like a cartridge filled with the affinity beads, for example, functionalized agarose beads. I think the most common example is the nickel NTA agarose. And you can just fill up your cell lysate in the column, let it flow through, like with gravity flow or with an FPLC system. You can wash the unwanted proteins away with your washing buffer and just elute your target protein with your elution buffer. And at the end, you have hopefully your purified protein. This is system one. Of course, for if you do not have an FPLC or cannot use the gravity flow system, there's another option, the magnetic beads. Magnetic beads itself are also agarose beads, but there are magnetic cores distributed in the agarose, as you can see here in this scheme and also in this microscopic images. So all the black dots are magnetic cores. So, but why is it nice that you have magnetic agarose? As you can see here in this purification scheme, you can also just put your MAC beads in your cell lysate, and the MAC beads can have, for example, a functionalization with an affinity, so an antibody or an NTA moiety. So there are lots of possibilities how you can functionalize your MAC bead to purify your target protein. You can add your MAC beads, just swirl it for a few hours, and when your protein has bound to your MAC beads, as implicated in the scheme, you can just add a magnetic field. You can get your beads with your bound protein on the side of the wall, like here, and just decant or pipette up your remaining cell lysate. So you can, of course, then wash your protein several times, elute it, and you will also get your target protein with a high purity from the MAC beads. So it's a really convenient system, especially for your lab work, but of course also in big scale systems. So this is, let's say, the next generation of protein purification. Of course, I can give you some examples for the affinity purification via agarose and MAC beads. So on the left side, you can see his GFP protein, and we spiked E. coli lysate with this. So you can see here the GFP band, you can see all the other proteins in the cell lysate, and finally, with our established indigo nickel agarose, you're able to purify the his GFP tag protein out of your cell lysate. So you can see all the other bands are no longer visible in the gel, and you're able to purify your protein with a really, really high efficiency. But what if you need a more sensitive binding or high specificity for your binding? Then you can also use, for example, antibody labeled MAC beads. Like in this case, we purified the membrane protein P2X4 isolated from insect cells using our high specificity Rho 1D4 MAC beads. So you can see here the lysate, the marker, and the purified protein from the cell lysate. But this is also, or this is of course only one option. So you can also use your own antibody, your own tag, and your own affinity moiety to functionalize beads. And this is maybe the most important point today, but I will explain it to you later on. So first, I would like to give you information about our nanoparticle functionalization service. So now we'll ask, okay, the purification. So you can purify your protein, but what can you do with nanoparticles, and why are nanoparticles interesting? So especially during the pandemic situation in the last years, so nanoparticles gained a lot of attention. For example, in the case of lateral flow assays. So this is maybe at the moment the most prominent example of gold nanoparticles. So the red stripe in your test are gold nanoparticles, which can be used in a kind of sandwich assay, antibody sandwich assay, to detect really, really sensitive like virus, proteins, and much more. So, and today, this gold nanoparticle service can include, for example, polymers, fluorophores, biological tags, antibodies, fab fragments, and nucleic acids, and much more. So, more or less everything is possible. But why are gold nanoparticles interesting? So, from a physicochemical point of view. So at the nanoscale, so most of the bulk materials change the physical properties completely. So like in the case of gold, it's no longer yellow and shiny, but it can be red, for example, a deep purple to red colloid. And this is because of the special interaction of materials with light on the nanoscale. So you can see here, for example, a gold nanoparticle and an incident wave light. And the particles are much smaller than the incident wavelength. So as described by, for example, Coulomb and the equations in the Maxwell equation, you can the incident electromagnetic wave will change the place of the electrons depicted in blue here, and the electrons will start to oscillate in this gold nanoparticle like a little nano antenna, and there is an electromagnetic field induced. So the most important point is that due to this oscillation, the gold nanoparticle absorbs specific light at a certain wavelength, which is related to the size and the shape of the gold nanoparticle. However, also the electromagnetic field can be used for the detection of molecules on the surface, like with a surface-enhanced Raman scattering. And due to this special optical properties, so a lot of applications are possible. Like here, as mentioned before, the surface-enhanced Raman scattering. So you can detect molecules. So you can detect one molecule on the surface of a gold nanoparticle, and it has a characteristic fingerprint. So like here, you can, for example, create a kind of barcode system on the gold nanoparticles. You can also use gold nanoparticles and the Rayleigh scattering of light in the optical coherence tomography, which would be, for example, a biomedical application. You can use the photoacoustic imaging, so the detection of gold nanoparticles in tissue, for example. You can also just release drugs at a certain spot in the cell culture, in the cell or in tissue. So just by using the absorption of light and the generation of heat directly on the surface of the gold nanoparticle. This can be, for example, coupled to a polymer, which will release the molecules after the absorption of light. Or you can use the lateral flow assays, as mentioned before, so kind of a sandwich assay. So because of this wide variety of application fields, so of course you need, every time you need a specifically designed and conjugated gold nanoparticle. So let it be one single nucleotide or nucleic acid on the surface, one fluorophore, or a set of polymers, like for the photothermal therapy, tags to label, for example, proteins in the TEM or antibody or fab fragment. So there are a lot of options and a lot of possibilities to actually functionalize the surface of the gold nanoparticle. But of course, a lot of know-how is necessary to achieve a stable conjugated system. So the nanoparticles, if they're not conjugated, are quite sensitive to environmental changes like buffer concentrations, pH. So it need to be specifically designed for the specific application. So I would like to summarize the features of customized noble metal nanoparticles. So in this case, as I said, gold, but of course other metals and also other not noble metals like iron are possible. So various sizes and shapes are available here at Cube, like spheres, like cubes, like rods. For example, rods are really interesting for the generation of heat. So for photothermal therapeutic applications, the rods are quite nice. If you have edges, you can use it quite nice for surface enhanced Raman scattering, or you can just use small spheres for the labeling of proteins, cells, particles, whatever you would like to do. As I said before, the design is quite important, and our service includes the assisted design. So if you have a challenge, we would be really happy to help you also while developing your design, so specifically for your application. Additionally, we have a state-of-the-art physicochemical characterization of the gold nanoparticles. So it is quite important to know the characteristica of your particles. So like the size, the hydrodynamic radius, the net charge. So for example, during the interaction with cells, so the net charge is quite important, or the protein corona. We can use standard agarose gel electrophoresis, also HPLC, and much more. So you can characterize your system like you would like to have it characterized. We can also do, for example, the negative stains and specifically detect the molecules on the surface. So, for example, with detergents or like ssDNA on the surface. So there are a lot of options. Of course, we have multiple ligand technologies in-house available. So maybe the solution to your challenge is already here at Cube available. So like antibody coupling, DNA, RNA, peptides, or chelating agents, drugs, dyes, natural ligands. So there's a lot of possible, and it depends on your application, what we can achieve with the nanoparticle construct. As mentioned before, the application field is really broad and is ranging from imaging, the TM, for example, nanosensors, drug delivery, lateral flow assays, and much more. So it's quite important to create the right particle design with aspects like the material or the functionalization to the question asked through the customer. Well, so the next point of the functionalization service is, of course, the agarose and MACBeat. And as mentioned before, we have Cube has a long tradition of protein purification, and the agarose and MACBeat service is quite important for our protein purification facility. It's more or less the same concept. So, but we does not use like noble metal or in general metal-based materials, but agarose and magnetic agarose. But the conjugation concept is more or less similar. So the features of the customized agarose and MACBeat service is that we have a broad range in size. So we can provide, for example, materials from 30 micrometer to run 1000 micrometers. So it depends on the particles you need for your experiment, like pressure resistance, for example, for the FPLC, or would you like to use gravity flow? So this is more or less the first decision which has to be performed. And also here are a lot of base materials possible, like organic polymers or agarose, but also other polymers like polystyrene and much more. So inorganic materials like the iron cores in our agarose or in the polystyrene particle are also possible. The conjugation chemistry ranges from like cyanogen bromide, which is really established since I think the 80s or 90s. Also epoxide chemistry or cutting-edge click chemistry. So also there is a lot of options for you to conjugate your affinity target or your moiety on the agarose for your specific purification challenge. We have a lot of ligand technologies already available, as you can also see on our website. So antibodies, peptides, chelating agents, drugs, dyes, or natural ligands, which are quite important. I will bring them on the table later. And also there is, of course, a broad application field, like for the protein purification. I think maybe the most point, or also specific applications like phosphoproteomics with our iron agarose, anti-agarose, or the nucleotide purification with silica particles. Or also you can do molecule depletion. So if you would like to, for example, remove a specific drug or molecule from a solution, you can also use the customized agarose or MAC beads to achieve this goal. We already had this. Right, so, but agarose bead, let me tell you something about the properties, because it's all about the properties of the agarose. And for example, the bead size. So if you have, for example, small affinity beads in your FPLC column, so you have a really high ratio of surface to volume. So which means you have a high binding capacity of your agarose. And also the agarose is quite stable to high pressure. So which means you can use a high flow through in your FPLC. However, you cannot use gravity flow systems, for example. Then you should use large affinity beads, which allows higher flow rates and also useful for viscous media. So also for batch purification and gravity flow, this is a quite nice solution. And depending on your workflow, we can implement the conjugation or the conjugation chemistry and your target ligand as you wish. The second example I would like to give you is the agarose concentration. So with an increasing agarose concentration, the protein exclusion limit is also decreasing. So let's increasing. So let's say, for example, you have a 9% agarose. So then you can the proteins with a size of up to 150 kilodalton can fit in the pores of the agarose. So it's also here in this scanning electron micrograph shown that the agarose pores are important, that the protein which you would like to purify can fit in. So if you would like to have a high binding capacity and have a small protein, then you should maybe use, for example, the 4% agarose. If you have a big protein like antibodies or huge complexes, then you should use, for example, the 9% agarose. But this is or can be implemented in your specific agarose platform. Another example is the cross-linking degree. So if you have, for example, a high cross-linking degree, so then it's quite stable for like mechanical stress. This, of course, will result in lower flow rate, for example, in the FPLC. So when you know your specific specific challenge. So then you can decide which cross-linking you would like to have. So high, low, in the mid. So, and you can of course implement this in the customized agarose. But there are a lot of examples, and to go through all would be quite challenging. So if you have questions, of course you can directly mail us and we can answer the questions or give you an idea how to solve your challenge. But I would like to give you a third example. So what we already, for example, achieved, and it was a kind of a great success story. So a client of us ordered a bulk amount of acetylcholine receptor, which he would like to use as an antigen for an experimental model. And he would like to purify this, but without the tag. So it's a tagless protein. And the solution was to conjugate a natural ligand of this receptor to our agarose. And this natural ligand is neurotoxin 3 from the cobra venom. So we conjugated it to the agarose and then we're able to purify with a high specificity this acetylcholine receptor from directly from tissue. So, and this was such successful that we implemented it or launched it as a product on our website, and it's still available. So you can find this, for example, as a acetylcholine receptor from Torpedo californica. And as you can see here, so by using a natural ligand to this receptor and our agarose and conjugate this natural ligand to our agarose matrix, we were able to purify this receptor. And this is true for many proteins. So if you have, for example, a membrane protein or protein in general, and you do not have a tag or are afraid that the tag will influence your protein, the stability or the downstream applications, so then it's also an option which you can just do in a customized resin. So to summarize our new service, so it's a new particle functionalization service from nanoparticles to micro agarose. So a lot of stuff is possible. And the most important point is that you gain control over your agarose, MAC beads, or nanoparticles. So this is the most important point, especially when you would like to, for example, develop a therapy with nanoparticles. So then it's necessary that you have a controlled system and a characterized nanoparticle system. We have here at Cube a huge set of base materials, ligands and conjugation routes already available, or can develop those species for you. Of course, the conjugation can be done with a broad range of materials. So you do not have to stick to MAC beads, agarose, or gold noble metals. So also like polystyrene particles and silica particles, and much more is possible. One prominent example is the purification of, for example, tagless proteins. So this was a great success for us. And of course, the controlled functionalization, and characterization of noble metal nanoparticles is really, really important for many applications, and especially for the biomedical research. And here at Cube, it's possible to even functionalize gold nanoparticles with one single molecule. So this is also an option for you if you would like to quantify, for example, something in your sample, so that you can be sure that your nanoparticle has only one molecule on the surface which binds to your target. Yeah, and finally, we are proud here at Cube that you can do everything from the proof of principle to the industrial scale production, and you can do it with us, and so with one partner. So it's also quite convenient for you if you go this way with us together. So finally, I would like to thank you for your attention, and I'm happy to answer your questions.
thank you, Michael. Do you want to put the camera back to big? Yes.
Great.
Cool. Yeah, really, really nice. May I ask the first question? Is this fine for you?
Totally fine.
As a biologist and as an enthusiast of cryotime, I was wondering. So, I mean, since a few years we came really down with the kilodalton sizes we can image in cryo. But the very small proteins are still a huge challenge. Could you use like this nanoparticle service to create a custom solution for a small protein, for example, to image such a protein and to get the structure?
Yeah. So the structure itself not, but you can. So there are, since I think a few years, there are a lot of papers out there which demonstrated that you can, for example, by using labeled nanoparticles with fat fragments, so they're really, really small, you can label, for example, specific proteins in cryo-TM images of cells. So you can label, for example, also lysosomes inside of a cell if you use these cell slides. So for the cryo-TM, then you can label specific proteins in cell images. You can use it, for example, also with really, really small gold nanoparticles, like 3 or 5 nanometer. You can use them to label specific sites of proteins and also demonstrate the interaction of proteins. So let's say you have one particle on the protein, then you have the same protein, and you add, for example, a binding ligand, which forms then a dimer. Then you can show in the TM, even if you cannot see directly your small protein, you can see that the proteins are interacting, and you can see that the proteins or the nanoparticles have a specific distance from each other. So there are several options, and there is a lot of literature out there which demonstrated this, for example, in cryo-TM.
Very nice. So in vivo and in vitro is both possible?
Yeah, more or less. So then you need, for example, other techniques, but it's possible, yeah. So on the cellular level, for example, in the coherence tomography, this is also done in the mice models. So there's a lot of done in the last 10 years.
Very nice. Okay, thank you. Let's go to the Q&A modus. And I could ask 20 more questions, but I think we go with the first question from Johannes. So does that mean if I find an agarose resin on the market, you can make a MacBeat counterpart?
I would say yes, more or less. So if you need a specific binding or specific ligand bound to an agarose, then we can develop a MacBeat pendant. Yeah, so more or less. So if it's not protected by patents, of course, so then we can do this. Yeah, and we did this a lot of times in the past and also in-house.
So if you can get your hands on it, you can make it.
Yeah, we can make it. Yeah,
cool. Next question from Cesar. Can you comment on fluorescent enhancement from functionalized gold nanoparticles?
Yeah, this is quite interesting and nice topic because I did this during my PhD time. So the electromagnetic field around the gold nanoparticles can enhance your fluorescence signal of a fluorophore nearby. But there are how can I say it? So there are some features which has to be provided. So it's important that, for example, the fluorophore is not too near to your gold nanoparticle surface, because then also the opposite effect can take place. So then your fluorescent signal can be quenched. So especially the design is then quite important. I think in the literature, for example, there are gold nanoparticle dimers used, and you need to specifically place at a certain spot in this dimer your fluorophore, but then you can enhance your fluorescent signal up to 300, 400 times. So this is possible, yeah, but it's a specific design necessary to achieve this goal.
Okay, next question, please. From Saba. Hi, I bought carboxymag beads XL for DNA purification, and recovery rate for DNA was so much lower in comparison to time that I purified them with SPRI beads. What can be the reason? Less density of the carboxy groups of the surface of the beads in comparison to smaller bead like SPRI? Maybe just answer this first and then I read the follow-up question.
Yeah. This is a quite good question, and to be honest, for this specific challenge, I have to ask our expert for the carboxymag beads. So we'll answer this question by mail, I think. So this is the best, I would say.
And then we're also gonna
So we have we have an answer, but we will write the answer by mail, I would say. So because it's a complex theme.
Okay, we promise we are fast.
Yeah.
Okay, next question.
Sorry for this.
From Sumia, I hope I pronounced it correctly. Is the magnetic Shitosan nanoparticle a core shell system? If yes, what is the size of the core or magnetic nanoparticles?
So magnetic Shitosan nanoparticles. So I think there are different options. So you can synthesize them as a core shell system, and the size of the core and the magnetic nanoparticles can vary. So, like for example, if you have, so you should use small nanoparticles or iron nanoparticles to avoid this magnetic attraction of the particles and the aggregation. So I would assume that in this case it's nanoparticle based. So not a core shell system, but nanoparticles which are functionalized to a bigger particle. But in this case, I have to look for the exact composition, to be honest.
Then we also go back to this. Okay, next question, please. Hi, maybe could you tell us a little more about the functionalization process?
Yeah, of course. So there are several options. So for example, you can have, if you have a gold nanoparticle, for example, so it's the common approach is to use, for example, a protective layer of polymer like polyethylene glycol, which is heterobifunctional. So on the one hand, you have a thiol moiety, for example, and on the other hand, you have like an activated group or another functional group which you can use to functionalize your nanoparticle further with the ligand. But there are several options. So of course, it's not necessarily polyethylene glycol. You can also use, for example, BSPP, so small ligands. You can use not only the covalent way of stabilization of your nanoparticle system, but you can also use the electrostatic way. So just physisorb your molecule of interest on the surface. So there are a lot of options. So, but normally we, for example, recommend to stabilize your gold nanoparticles covalently to assure that you will have a colloid which is stable in like biological buffers, for example, and which are quite rigid with respect to pH and temperature and of course the time. So there's not one functionalization process in general, but it all starts from the particle, and then you can build up your functionalization step by step. But it depends on your application. So, for example, if you need a really small nanoparticle for like staining of tissue, so then your conjugate should be quite small. So then you cannot use like large molecules because then the hydrodynamic radius of your particles would be really high. So it cannot reach like deep in tissues or in cells. So there's not one general answer, but a lot of options. So it depends on what you would like to do.
Yes, very elaborated answer. Okay, I think we have time for one more, and then the rest we of course are going to answer afterwards via email. From Clara, Did I get that right? You can functionalize the beads to a single molecule? Please confirm.
Yeah. So we did that in the past, and it's possible. Yeah. So this is a really advanced conjugation method, but we achieved this and also in larger scale. So this is quite nice for, like, as I said before, quantification of your target, labeling of one specific molecule with gold nanoparticles. So yeah, it's possible, and we did this successfully in the past.
Yes, I think this is a good note to end. You see, service is worth it. If you're interested, get back to us. We are ready to help you, ready to develop the service pipeline together with you. And you can see Michael is super excited for it. He really wants to go for it. The rest of the many questions we, of course, are going to answer, as we said. Thank you very much for staying with us and for listening to this talk. And we are looking very forward to see you in the next masterclass. And if you are now hot to see more of our Intelligent Infusion masterclasses, you can always check our YouTube channel. Just go on YouTube and put Cube Biotech or just Cube Biotech in it. And we have our own playlist, and there you're going to see many, many cool, interesting talks about polymers, about membrane proteins, about proteomics. It's really a broad range. Feel free to check that out. And we really hope to see you next time. And with this, thank you very much. Thanks, Michael.
Thank you for your attention.
And see you around.
See you next time.